The reason why I started in the steel industry was because I wanted to revolutionize it. I noticed that at university and at any other manufacturing plant there's plenty of CNC machinery, robots and the likes. And suddenly I stumbled across the steel industry, and every company, at least in London and vast majority in the UK, were working manually. So tape measure, scribing, punching and drilling manually, and that really shocked me. I was like, wow, I mean, this can't be the way to fabricate structural steel. So that's how I started the company, with revolutionizing in mind. So I thought, I was disillusioned. I thought it will take me 2-3 years to achieve a level where I'll be proud of that. Yes, we do offer a really good service, but it actually took us probably 6-7 years. It's only when we moved to this place that I was like, okay, fine, this is how a structural steel company should operate, with all the machinery and also the infrastructure in the background, which is our IT system, which we've developed ourselves because we couldn't find a ready-made software. We've also got another unit exactly the same size as this one at the back, and that's where we keep our stock for very short turnaround. So that's why we're able to have fabricate for next day if required. So revolutionizing is the core of why Steelo exists. We operate based on our Decalogue. It's a set of 10 values or way of doing things. And this is what brings us all together. So everyone who works here shares our values, and we also work with customers, suppliers, partners who share these values. We basically don't want to work with people who cheat or are not transparent. But to the outside world, we want to be known as the reliable company, as someone that provides, they deliver on their promise. And this is, it sounds easy, but it's not, because reliability is a challenge.
Good afternoon, everybody. My name is Lina and I'm a design engineer here in Steelo, and part of my job is also to coordinate a 3D printing project that we recently undertook. A little bit more about additive manufacturing. So basically, additive manufacturing is a technology that enables us to produce 3D objects by depositing material layer by layer. It's gaining quite popularity. It's becoming popular because it's proven to reduce production time, cost, and material waste. And at the same time, it enables us to design and develop complex shapes and geometries. So as you can see, 3D printing is actually happening. It's also happening in construction. And because here in Steelo, we're always looking for innovation, we wanted to engage ourselves with a 3D printing project. So as Michael mentioned before, we sponsored a master thesis by Cranfield University in collaboration with Cranfield University. And the reason behind it was that because there is a lack of skilled welders willing to work in the industry, we need to move towards an automated era. So this is why we started looking at what we can actually 3D print. And our main focus was actually in the connections, because this is where our added value cost is. And the project was basically to 3D print end plates on an eye section. I've got the sample here, if you would like to touch it and just rotate it around to have a look. The technology we used is a wire and arc additive manufacturing, well known as WAM, and I will explain a little bit more about it. So WAM is basically an automated welding technology. It uses the exact same components used for automated welding. And everything can be purchased off the shelf, so it's quite, it's cheaper than most AM technologies. And how it works, it combines an electric arc used as a heating source, and the wire, in our case it's structural steel, is used as the consumable electrode. And the motion is provided by either robotic systems or computer numerical control gantries. So the main focus was to basically 3D print an end plate 150 by 150, just to prove that we can actually do it. And we did it quite fast as well. So the material was deposited layer by layer, starting from the middle of the section and moving towards the outside of the beam. And the student who was responsible for it did all the crystallography and all the measurements to see how this reacts. And there were some events like lack of fusion, porosity, that were overcome while repeating the process. But because this is a project that's quite new and it's at its infancy, we want to see what's more there, what more we can do. So definitely there is future work to be done. And basically we want to see what other types of connections and bespoke structures we can create. And that's why, as Michael mentioned before, we collaborated with Foster and Partners, Cranfield and Warwick University, Global Robots, who will be supplying us with all the technology equipment, and Lloyd's. And we've applied for an Innovate UK funding in order to push further the project and see what else we can do. And what we're basically trying to do is not just to 3D print something that looks good. We want to actually certify it and put it on site so that it can be used and move construction into a new, let's say, state of mind.
My name's Luke. I'm one of the designers here, the detailers. And I'm going to be talking about how to design steel that will fit safely on site. So here at Steelo, we aim to make the journey of steel as safe and as easy as possible. And a big part of that is we try and foresee any problems the builders are going to face and resolve those problems before the steelwork shows up on their doorstep. So we're going to look at some common issues encountered when going from the theory to the practice, to the reality of steel. So we'll consider crank beams, beam selection, plate selection, weld design, how you design your bolts, designing for installation, and then we'll have some questions at the end. When considering a beam to use, there's lots of different profiles you can use. Obviously, as a structural engineer, when you're deciding what beam to use, you may consider the loads, you may consider the weight of the beam, you may consider the profile and its size. But size in particular can be a problem in design because sometimes a profile's name is misleading. So for example, the humble UC 203, 203, 46. Now the first 203 there denotes the height of the beam. The second 203 denotes the width of the beam. And the 46 denotes the mass per meter, which is 46 kilograms. So then you would expect, if that's the case, when you see a UC 203, 203, 60, for the height to be 203, for the width to be 203, and for the mass to be 60 kilograms. In reality, though, that's not the case. So in the middle here, we have an actual 203, 203, 60. And you may not be able to read this, but I'll read it to you. The height is 209.6, and the width is 205.8. The third one is 203.86, and the height of that is 222, and the width is 209. So all of these are called UC 203, 203, but in reality, the size of the profile is very different. But sometimes when a structural engineer provides us with a drawing, it's assumed that the two UC profiles, even though one's a 46 and one's an 86, are the same size, when in reality, there would be a 19 millimeter difference in the size of those beams. So what we do when we get a drawing like that is we'll call our client up, we'll explain the situation to them, and we'll ask them, do you want these beams to be flush on the top, or do you want them to be flush on the bottom? So as we're modeling our steelwork, we're constantly thinking about our clients trying to install the beams. And we're thinking about how easy that's going to be, where there may be difficulties and issues. And as Melina has already mentioned in her presentation, we will often advise our clients to use a splice if we can see that a beam is going to be long and difficult to install, and sometimes impossible to install. But another particular design which throws up problems, all sorts of problems, is double beams, so two beams next to each other. Here's an example from a project that I was working on the other day. Here are two beams next to each other, 203, 203, 86 beams, two of them next to each other. And on the end we have another beam coming off, a single beam, which is attached. And you can see it in this graphic here. That's the double beams with the other beam coming off the end. And on the left-hand side of this image here, you can see the connection. So there's an end plate which spans between the two double beams, and the beam which is coming off them is attached right in the middle. Now, this throws up two problems. The first problem is that this end plate, which goes all the way around the columns, around both beams, is going to have to be welded on both beams here on site as we fabricate it, which means that the beams will have to be delivered together, attached, which is going to be a big issue because these are long beams and they're UC 203, 203, 86. They're quite heavy beams. So delivering two of them together is going to be an issue for our client. So when we see that, we can suggest to our client a few things. On this occasion, we suggested perhaps it would be better to have this end plate welded on site. So we'll deliver the beams separately, you can install them, and then afterwards you can weld that end plate on site. That's the first problem. The second problem is that once the beams are installed, the bolts will be inaccessible. So you can see where the bolts are here. It's going to be impossible for the client to actually reach in between those two beams to attach the nuts to the bolts and tighten it up. Is that clear? So the bolts are going through here. These are double beams. It's going to be impossible to reach in between them to tighten the nuts for the bolts. And so that's another issue which the client's going to face. So on this occasion, we suggested to him, you can either use a form of blind fixing, like a hollow bolt, or we can weld nuts on the inside of the plate, and then you'll be able to screw in the bolts from one side without having to access the other side. And on this occasion, he talked to the engineer, and the engineer advised to use blind bolts for that connection. But that's a problem which hadn't been thought about by the engineer prior to him making his drawings. And that's a way that we can help the client by not just delivering it and then leaving him in a place where he can't actually put the beams together.